Thank you so much for being here tonight. It is a true honor. I need to start this talk with a little bit of a confession, which is that I cannot code. And that might not be what you were expecting to hear tonight, given the title of my book and the topic that we're discussing. But it's true. If you show me a screenshot of code, unless it's something extremely basic, like hello world, or a birth date calculator, the things you learn on the first day of a programming class, I'm not going to understand it. In fact, I would wager a whole lot of you here tonight know code far better than I do. Nevertheless, I've spent a pretty good portion of the last few years of my life devoted to the ways that code intersects with our lives. And, more importantly, how humans produce code, how they write it, how it goes wrong, how it goes right, and how it affects all of our lives. Programming and the decisions around it undergird our cars, our banking systems, our financial systems, which are our banking systems, our schools, criminal justice, employment decisions, public policy, and social safety nets. I think that we like to think that code is something almost clinical, that it's preordained. It works that way because that's how it was meant to be. But in code, there is no meant to be. It's a series of decisions. Whether you're a coding wizard or, like me, you don't know your JavaScript from your Python, I hope that you'll leave here tonight with a better understanding of how each piece of software, consequential or not, is made up of that series of decisions. Decisions that reflect humans' biased, messy, short-sighted, yet often brilliant thinking. I think it's important for even the non-technical among us to understand that code is infused with human values, and it's really critical for technologists to sometimes take a step back, to think about how their work affects people, and even listen to people who don't know how to code, just once in a while. As Lisa said, you are not expected to understand this describes 26 lines of code, both figurative and literal, that have changed the world or reflect something about the process of creating code. It covers the first pop-up ad, a code error message that nearly aborted the first mission to the moon, a t-shirt with a snippet of code that made it technically violate US government export controls, even internet relay chat, for those of you old enough to remember IRC like me. It's written by technologists, historians, journalists, human rights advocates, and others who work closely with technology and care about not just producing a product, but how that product affects people. Of course, the book has a rather provocative title, one that I'll explain a bit in a bit. And in a way, I think it belies my personal belief, which is that everyone should be expected to understand the basic way that code shapes our lives and how it's built. And on the flip side, that the tech industry has a lot to gain from adapting some humanities thinking. I'd like to back up a bit now and tell you how I came to edit this book. I said I don't know how to code, and that's very true, but it's not for lack of trying. I first learned about the power of software as a teenager when I was about 14, from two things: pop music and a near apocalypse. We're going to start with the Backstreet Boys, which is, I'm sure, what you were all expecting tonight. Yes, the Backstreet Boys, and you can't shame me more than I have shamed myself over this over the years. When I was about 14 in 1998, I became a huge fan. No one else in my life would admit to liking them. I still think they were just hiding it. So to find other people who would let me talk to them about the Backstreet Boys, I went to this new place called the World Wide Web. And there, I found lots of people who would admit to liking the Backstreet Boys, at least from the safety of their computer. The coolest among them had websites hosted on sites like GeoCities, AngelFire, and Tripod. And I decided I had to be one of the cool people. I wanted my own Backstreet Boys site, a Backstreet Boys fan fiction site, no less. Now, today, if you decide to build a website, fan fiction or otherwise, God bless you if you do, you get to use an editor that's what we call WYSIWYG. What you see is what you get. And it works a lot like a word processing program. If you want to bold something, you just hit that bold button. But back in the 90s, you had to do it yourself. So I had to learn hypertext markup language, or HTML. And that's what's telling your browser what to do. The WYSIWYG editors do that for you. So I bought books, I scoured the internet, and I learned. That meant that tweed-in teenage girls from around the world could come to my website where they could feast their eyes on this sort of seafoam green marbled background with black text that broke all the accessibility rules. I'm amazed that anyone bothered to read it. And there, I posted my terrible stories about Backstreet Boys falling in love with me and my friends. And then I started posting other people's terrible stories about the Backstreet Boys falling in love with them and their friends. And in time, and I don't know why I insist on telling people this, I created one of the biggest Backstreet Boys fan fiction sites online at the time. But I really loved, when I stepped back and thought about it, how HTML gave me the power to give instructions, not just to one computer, but to every computer that navigated to my site. If I wrote that I in little carrots, the text would become italicized. If I forgot to close that I, then all of the text that followed would be italicized. If I forgot the R in the ahref part of a link, that link wouldn't work. And normally, I would be linking to another person's Backstreet Boys fanfiction website per an agreement. If I linked improperly, that person would be angry because we would have agreed to link to each other. As a side note, I'm not the only person who learned some tech and online organizing skills from fandom. I highly recommend Caitlin Tiffany's recent book, Everything I Need, I Get From You, How Fangirls Created the Modern Internet as We Know It, which is a little bit more modern. That's about One Direction. As I was teaching myself HTML, something else was going on that was slightly more significant, Y2K. For those of you who might be too young to remember, basically, in the 20th century, computer memory was very limited. In fact, your iPhone has more than 1 million times more memory and RAM than the computer that took the first mission to the moon. So, an easy way for programmers to save space was to code years with 2 digits instead of 4. That meant that computers assumed every year started with 19. And that worked great in the 50s, 60s, 70s, and 80s. And then we got to the early 1990s, and people started to realize that that could be a problem as we approached the year 2000. The big fear was that we would hit January 1st, 2000, and computers would think we had gone back in time to January 1st, 1900. And that would cause a whole lot of problems. I think sometimes, especially if you're a teenager, it feels like the year 2000 was a technological dark age. But even 23 years ago, computers were really central to our lives. As fear about Y2K began to spread, people were worried that electricity might stop working, planes might stop flying, government payments wouldn't go out to people who needed them, the banking system might collapse. Doomsday preppers started to stock up on food and supplies for the virtual end of the world, or the end of the virtual world, you might say. Now, most people realized that the world wasn't really going to end, but that didn't mean everything was going to be just fine. So governments, companies, and individual programmers raced to update computers before we hit New Year's Day. And in the end, it mostly worked. There were some problems when the calendar turned to the year 2000. Most of them were fairly small scale. So, for instance, some ATMs malfunctioned. One of my favorite examples, slot machines at a racetrack in Delaware in the United States stopped working well. But there were some more serious problems as well. Here in the UK, within the National Health Service, people in a very small geographic area pregnant women who were being screened to see if their fetuses were at risk of Down syndrome, the screening program worked incorrectly. It calculated their ages wrong. And that meant that several women ended up finding out very late that their babies did have Down syndrome. For most of us, though, things went along pretty much as usual. And a lot of people thought, or still even think, that that meant that Y2K was overhyped, that it was never really going to be that big of a problem. But that wasn't the case. Y2K didn't become a huge problem because programmers saw the threat was coming and they fixed it. And in my mind, that made programmers a hero. Between the Y2K heroics and my self-perceived wizardry with HTML, I thought computer science was the future, and maybe part of my future too. So when I was in 10th grade, what you would call year 10, I decided to take a C++ class. The course catalog said that there were no prerequisites. You didn't have to know a bit about coding to take it. I thought I would ace it. And then I had the first day of class. I was the only girl in a class of about 20 boys, and all of them, it seemed, knew exactly what they were doing. Most of them had learned programming from their parents or from their dads and were just trying to add a new programming language to their repertoire. My mother had actually coded a little bit in the 70s when she was a management consultant, but she hated it. And later I asked her, how could you let me do this? And she said, I thought you would do better than I would. And I showed her. So I flailed. I thought my HTML background would help me, and I couldn't understand what was going on. Now I understand the problem. HTML, under one definition, is code. It gives instructions to a machine. But a better definition of code, or a more modern one, is that code has to compute something. So HTML wasn't really code. It was a really, really basic idea that I didn't know. My class, though, was filled with people who did understand that. So we didn't bother with that sort of introduction, what are we doing here? My teacher was a woman who seemed to think that I was single-handedly going to hold back all girls and women in computer science everywhere. So she just sort of wrote me off pretty quickly. Sometimes when I was really stuck, the boys would just fix my code for me very kindly. They were all very sweet. But it was clear to everyone in that room that I had no future in computer science. So when I went to university, I decided to study English, which is the final refuge of the non-technical. Eventually, I became a journalist covering all sorts of topics. And then eventually, that led me back to tech. In 2011, I began working as the editor of Future Tense, a partnership of Arizona State University, Slate Magazine, and New America, which is a think tank in Washington, D.C. The goal of Future Tense is to cover the intersection of technology, policy, and society. And when the good folks at Slate, ASU, and New America told me about the job opening and asked if I was interested, I said, absolutely not. I remembered that coding class. How exactly was I supposed to help cover artificial intelligence and cybersecurity if I couldn't even limp through a C++ class? But ultimately, they told me, and I think this was right, that it was actually a benefit for me not to have a strong technical background. They pointed out that the readership we wanted to reach was people who weren't necessarily experts. The idea was to help citizens learn about the future, to help them take part in the discussions about the technologies that were going to be so important to them going forward. My non-technical background let me be an advocate for them. If I didn't know what a computer scientist was writing, then our reader wouldn't either, and so I could ask that question for them. So I began editing opinion and analysis columns by academics and other experts who were interested in educating the public. I also started to meet technologists who desperately wanted to work with somebody like me. They told me, to try to break out of their bubbles. This is around 2011, 2012, when, as you may remember, the hype about technology was huge. Tech was going to fix everything. And I was meeting people who worked in Silicon Valley and told me that they were starting to really get worried that computer scientists were only talking to each other. They weren't actually listening to what the rest of us might want from tech. They just wanted to solve problems without thinking about the human. In 2019, a colleague of mine at Slate began reading the coverage of the coding error that contributed to the crashes of Boeing 737 MAXs in Indonesia and Ethiopia. It was a terrible tragedy. More than 300 people died. My colleague thought that it might be illuminating to collect other examples of places in which a tiny coding error had huge consequences, huge negative consequences. I thought it sounded great too, so I volunteered to lead the project, which would end up becoming both a series on Slate and then this book. So to get started, I sent a lot of emails. I surveyed almost 200 technologists, historians, journalists, human rights advocates, and others to find out what error in code did they think had had the biggest consequences. I also asked them to provide a little snippet of the code if they could. And, well, technologists can be pretty blunt, and they quickly told me that I was so misguided on this. They told me that, yes, if we looked for small errors in code with big consequences, we'd find other examples. Some of the other famous examples are that in the early 1980s, the Vancouver Stock Exchange software had a tiny rounding error that ended up making the exchange lose a pretty significant amount of its value until someone realized what was going on. And then the exchange had to shut down for a little while to fix it. A couple years later, in a more tragic example, there was a radiation machine used to treat cancer patients. A coding error meant that it gave patients a far too large a dose of radiation, and at least 3 people died as a result. But in a grim way, these errors, the Boeing 737 MAX, the rounding error in the Vancouver Stock Exchange, the Therac, the radiation machine, they were all sort of the same. Small error, big problem, and the message is just be careful. In the end, that doesn't really tell us that much new. What would be far more valuable, I realized, was to mix those sorts of errors with more figurative lines of code. And when I expanded the scope of what we were looking for, the experts had a lot more ideas, including internet lingo, famous comments in code, the birth of a coding language, the structure behind Wikipedia, and all sorts of other things. Digging through those suggestions took months, really thought-provoking months. And the end result was a big package that we covered, published on Slate in October 2019 called The Lines of Code That Changed Everything. And the spine of this package was a list of 36 blurbs written by both experts and journalists at Slate about all sorts of significant coding moments, beginning in 1725 with the birth of the punch card, or binary code, essentially. We also published a handful of essays about topics that were a little bit hard to boil down into 200 words. So there was an example about binary code, the gender binary, and the huge effort that it's taken to update large institutional databases, many of which were coded decades ago, to reflect more than just male and female. Another looked at hello world and the spark of joy that comes when you code your first successful program, a spark that I don't identify with, but I really wish I did. It sounds fantastic. We also had one from Slate's excellent vice president of technology who wrote about how it's so difficult for programmers to code, not just for next week, but for years into the future, an idea that I'll be coming back to a lot tonight. Now, if you've ever found yourself a little riled up by a list of the best 50 songs of the past 50 years, you know that the purpose of an online list is not really to be definitive, it's to get you arguing. And this list did that. So we had lots of technologists, some of whom did not respond to my initial email, saying, why didn't you include this? Or I disagree about that. And the online conversation kind of helped us decide that we could make a book out of this. The good folks at Princeton University Press agreed, and nearly 4 years later, here it is, thanks in no small part to Hallie Stebbins, the fantastic editor that I worked with at Princeton University Press, and it features beautiful illustrations by Kelly Chudler, which you'll see some more of tonight. The book has a whole lot in common with the original package, but also several new ideas and new writers, and of course it's expanded. And now I think it's 26 essays that can offer something to both non-experts and experts alike. Now I'm going to go through some of the examples from the book and the way they can help all of us understand a little bit more about how good intentions in programming can have bad consequences, and why it's so important to bring humanities thinking, even from failed computer scientists like me, to software engineering. Our first story comes from Ethan Zuckerman. Back in 1997, a couple of years before I would become a pioneer in the highly competitive world of Backstreet Boys fan fiction, Ethan was a young programmer at Tripod. Tripod was one of a handful of services that would allow users to create their own personal web page, which was a pretty new idea. The services were free. They were free because, as now, the services could add ads to your website. Now, the online advertising ecosystem was very different then. Today, if you look at a pair of shoes online, they will follow you around for weeks. Back then, you couldn't even really buy shoes online, and if you could, they certainly would not be able to target you or follow you that way. Much to advertisers' dismay, they had no idea where their ads were going to appear. And in fact, even now, that's a difficult problem. Every now and then you'll hear about, say, a controversial YouTube influencer who says something that creates a firestorm, and then advertisers get very angry when they realize that their brands are appearing as pre-roll on that person's YouTube page. So, 1997. Unfortunately, if you give people the opportunity to create whatever they want online, some people aren't going to be terribly wholesome. In fact, even Backstreet Boys fan fiction got pretty racy at times, which was horrifying to me at the time. So, 1997, Ethan Zuckerman's boss at Tripod tells him they have a big problem. An auto company has discovered that their ads are appearing on a website devoted to a rather adult recreational activity. Ethan's boss asked him to find ways to sell ads while ensuring that brand managers wouldn't send him outraged screenshots of their precious brands appearing alongside offensive content. So Ethan had an idea. He wrote the line of code that you see here. This code was inserted into the top of every homepage hosted by Tripod. And when it loaded in your web browser, it would launch the page you wanted to go to, but also a second window. And that second window included some Tripod branding, some tools to navigate between user-generated pages, and, critically, a 200 by 200 pixel ad. This was probably the world's first pop-up ad. And as Ethan puts it, and you are not expected to understand this, the result was, presto, plausible deniability. The pop-up was his solution to the thorny problem that the internet still faces. How can advertising support user-generated content? Just a couple of weeks later, Tripod's leading competitor, GeoCities, copied Ethan's code and used it to launch a similar website. As Ethan points out, this didn't exactly require sophisticated corporate espionage. You could just hit view source in your browser and see it. That's how lots of JavaScript programmers learned their trade. That's how I learned a lot of HTML. Not long after that, Ethan writes, he saw a pop-up ad with only an ad in it, no separate branding or navigation tools. And then came pop-up ads that would move around the screen as you tried to close them, which was fun for like 3 seconds. Then there were pop-unders that would appear underneath your web page, so you'd think you had made it through unscathed until you closed the window and found the pop-unders. And then there were cascades of pop-ups, just one after another, until, as Ethan puts it, you would wish you had never heard of the internet in the first place. The worst was when you encountered basically the opposite of the problem Ethan was trying to solve. You went to a perfectly wholesome-looking page, only to have a rather explicit pop-up ad attack you. Now, some of you may have lived in an internet pretty free of pop-up ads, because browsers are very good now at keeping them from, well, popping. But for those of us old enough to remember, the pop-up ad was like a little bit traumatizing. I think we're all a little bit scarred by them. Ethan learned about that collective trauma in 2014. That year, he wrote an article for the American magazine, The Atlantic, about what he called the original sin of the internet, offering users free content in exchange for monitoring our attention and surveilling us. It was a very long essay that included that little short aside you see there. I wrote the code to launch the window and run an ad in it. I'm sorry, our intentions were good. A very savvy editor at The Atlantic noticed that little nugget and realized that that was something people would really want to read about. So, in addition to the long article, she published a very short item on the website with just a little, that part about the ad and an extra quote or two from Ethan. So, now there are 2 articles running on The Atlantic's website. The first is a 4,500-word thoughtful exploration of the internet ad ecosystem. And the second was about 260 words made up of 2 or 3 quotes. Guess which one ended up getting a whole lot more readers? The apology ricocheted across the internet. It even appeared on late-night talk shows. Mostly, it generated wry laughs. Most of us have recovered from this trauma. But some people were genuinely furious. Ethan has experienced actual death threats and swatting as a result of this. In case you don't know, swatting is when someone will falsely call police and say there's an active hostage situation going on so that the police will go and try to stop it. It's incredibly dangerous. Ethan, understandably, is pretty sick of talking about the pop-up ad. But he agreed to revisit it for this book for one reason. Since he apologized, many technologists and business leaders have told him that he's taking on far too much blame here. As they put it, his code wasn't exactly groundbreaking. It was clever, but if he hadn't done it, someone else probably would have, or at least something quite similar. So does that very likely scenario, Ethan wants to know, mean that no one was actually responsible for the pop-up ad? That it was just capitalism, not the action of a single person? Ethan could take that out, but he's someone who feels a great deal of responsibility. He says that the problem with refusing to accept personal responsibility for making the internet a worse place is it means that no one is responsible for making the internet a better place. The internet is built on this system of surveillance capitalism, monitoring us all, turning us into data, and then both selling that data and using it to advertise to us. If the emergence of surveillance capitalism is diffuse, then it's a force of nature. It's unstoppable and incomprehensible. But if it's actually the sum of small decisions made by self-interested actors, then it's understandable and maybe it's reversible. Today, in a sort of penance, Ethan's working at the University of Massachusetts and is trying to create a version of social media that doesn't watch you, predict your behavior, and target ads to you. But I wonder, even if the pop-up ad wasn't inevitable, was it unethical of Ethan to code this? It would have been really difficult for him to imagine how a single pop-up would spread through the internet, causing endless amounts of frustration and even spreading malware. It's a demonstration of how decisions that end up having big ramifications don't seem all that important in the moment, in coding and elsewhere. Ethan wasn't really trying to transform the way internet ads were displayed. He just wanted to keep from losing that auto company as a sponsor. The difficulty of long-term thinking in code brings us to our next example of a programming decision that have consequences for decades to come. But this one is far more serious. This example demonstrates how computer systems, far from being somehow objective, reflect human values, biases, and blind spots. In You Are Not Expected, Charlton McIlwain, who is a historian of technology and administrator at New York University, writes that in the early 1960s, as the Black civil rights movement raged across the streets, there was a quest to build a more racially just and equitable society. And that happened right alongside the computing revolution. Soon, those two would fuse in a software system to help police departments collect crime data and then use it to determine where to focus crime-fighting efforts. It's a decision that would end up deeply affecting our society even today. In the early 1960s, IBM topped the list of the world's leading computing companies. It not only innovated new computer hardware and systems, but new ways of thinking about the computer's role and utility in everyday society. In IBM's 1965 annual report, the company president defined the computer as essentially a problem-solving tool. The company's marketing representatives didn't peddle prepackaged products. Instead, they asked leaders in every leading industry what problems they faced and how IBM could solve them. And while IBM labored to market new computational solutions to social problems, uprisings were happening across the United States. One of the most famous of these took place in 1965 in the Watts neighborhood of Los Angeles. After one too many incidents of police brutality at the hands of the Los Angeles Police Department, there were 6 days of unrest. Hundreds of police officers flooded the streets, 14,000 National Guard troops were deployed, 34 Black residents were killed and thousands more were injured, and more than $40 million in property damage occurred. Just 2.5 weeks before the Watts uprising, President Lyndon Johnson formed the President's Commission on Law Enforcement and the Administration of Justice. The commission's goal was to study the causes of and find solutions to America's crime problem. In the spring of 1966, following the Watts uprisings, Johnson added the Science and Technology Task Force to the commission to introduce new computational solutions to crime. The task force was led by Saul I. Gass, a mathematician and operations research pioneer who had been managing all of IBM's federal research projects. And the central focus of the task force became the police beat algorithm, a snippet of which you can see here. It was designed to help police departments divide up municipal areas and determine how to deploy resources in those areas. Doing so relied on 2 primary components, the availability of crime data, and one primary component, the availability of crime data, and 2 key computational techniques, norming and weighting. Norming refers to analyzing the data to determine the normal and aberrant levels of criminal activity, both across geographic areas and across specific populations of criminal suspects, such as white people versus Black people. Weighting, in this instance, was a means to rank the severity of different crime. So, for example, homicide, rape, burglary, larceny, and auto theft were all weighted with the same score of 4, signifying the most severe forms of crime. But these weights were arbitrary or even biased, as Charlton writes. The geographical areas were weighted by the preponderance of crime committed within its boundaries. The crime data, the statistical norms, weights, and geographical configurations all figured into the police beat algorithm. So in one respect, the police beat algorithm was developed to address a problem that framed Black people, primarily those who were poor and lived in urban areas, as predominantly responsible for crime, and as a result, the problem that needed to be solved. The police beat algorithm was therefore geographically determined to locate, isolate, and target Black and brown communities for police profiling and surveillance. And if they were more policed, more crime would be caught. And that meant that they were just taking the history and projecting it onto the future, creating a reinforcing cycle in which they just kept being policed more and more. Essentially, this was a proof of concept, but it was actually implemented in 1968 in the Kansas City, Missouri Police Department. And it's through that system that we first saw the disparate impact that the police beat algorithm had. The algorithm led police to make the tactical decision to concentrate on East Kansas City, which housed most of the city's Black citizens. And ultimately, the police beat algorithm became thousands of similar systems that now include facial recognition, mobile surveillance, and other tools. And the same logics and assumptions that permeated the police beat algorithm now show up everywhere from local law enforcement to international security. Today, when we talk about law enforcement algorithms, people really like to invoke Minority Report, the 2002 Steven Spielberg movie in which somehow a system can determine to the second when a crime will occur and who will commit it. In fact, when I was editing technology coverage, I made a rule that you were not allowed to invoke Minority Report because I just got really tired of it. I also got really tired of Terminator references and artificial intelligence. We can talk about that later if you'd like. But the problem, not just me getting bored with it, is that I think that the comparison confuses people. In the movie, AI works basically as though it's magic. We really don't know exactly how it happens that this system made up of these three people with these things on their head know exactly when crime is going to happen. But in reality, we know exactly where that ability comes from, as Charlton describes. It comes from that mapping the past and projecting it onto the future, except more so. But when we talk about AI as though it's magic, it makes it much harder to actually regulate it. It's also worth knowing that one of the few good things about the police beat algorithm is that we do have the source code. We know how it works. We knew that homicide and auto theft were weighted in the exact same way. Today, most of these systems used by law enforcement are proprietary, and they don't release that source code. So we have no way of knowing exactly how these systems, whether in fact they're in criminal justice or other systems that affect our lives, actually work. And that's, I think, a real problem. So now we have one more example of code going wildly wrong. In the late 1980s, a handful of computer scientists began voicing concern about what could happen if a rogue program were released on the network. But no one was prepared when it actually happened, as journalist Katie Hafner writes. This is Robert Tappan Morris, and at 8:30 in the evening of November 2nd, 1988, Robert was a 23-year-old Cornell University computer science PhD student. And he accidentally unleashed just such a program. It was really intended as a harmless hack, just to prove that it could be done. His program was supposed to copy itself from computer to computer and then hide in the background in as many machines as possible so that it couldn't be detected. Morris used several bugs he found in the Unix source code and designed the program to lead the list of users on a target computer. And then it would run through their names, permutations of their names, and common passwords. Incidentally, in 2022, the maker of a virtual private network released a study that found that the most common password in the world was still password. The number 2 most common password was 123456. And the number 3, for people who wanted just a little bit more security, 1234567889. If you were using any of those passwords, no shame. I think that shame is one thing that holds us back in cybersecurity, but please change it. Use a password manager, they're beautiful. So back to Robert Morris. When his program guessed the password, it would then sign on to the computer and masquerade as a legitimate user and copy itself onto the remote machine. Not only did he have no intention of crippling the internet, but he had actually tried to devise a way to keep it from propagating too swiftly. Once the program entered a computer, it would signal its arrival to the machine and ask whether that machine had already been invaded. If the answer was yes, the 2 copies would talk to each other, flip an electronic coin, and decide which one should stop running. And this is where Robert got into trouble. What if someone discovered the intrusion and tried to trick the incoming program into believing that it was already on the machine it approached, which would essentially vaccinate the computer against the intrusion? Thinking like a chess player, Robert Morris decided there had to be a countermeasure against potential vaccination. His solution was randomization. That is, that 1 in n times, the program would enter a computer and command itself to run on the target machine, regardless of whether a copy was already there. And then he went to dinner. Unfortunately, the number that Morris chose for n was 7. And that was a fatal miscalculation. The number should have been higher by a factor of at least 1,000. Because the number was so low, the result was that sometimes dozens or hundreds of copies of the program would appear on the same machine. By the time he got back from dinner to check on the program's progress, Morris realized that he was in deep trouble. It had spread wildly out of control. He even panicked and called a friend at Harvard and asked him to post this message on the network. The friend posted the "I'm sorry" and the way to address it. His friend noted that he hoped it was a hoax, but it most certainly was not a hoax. Computer managers stayed up all through the night trying to fend off the virus, which was later reclassified as a worm for the pedants in the room. It hopped back and forth around the internet. People were also frantically trying to make their network safer because they were worried that this was just the first in a new salvo of attacks. At one of the computing facilities at UC Berkeley, someone taped a sign that read "Center for Disease Control" on the door. Within hours, the program had crashed thousands of computers across the United States, at universities, research institutions, and, unfortunately for Robert, US government. Morris ended up being charged with a single crime under the 1986 Computer Fraud and Abuse Act, a law that was itself interestingly inspired partially by the 1983 Matthew Broderick movie War Games. In that movie, Matthew Broderick breaks into a federal computer. Morris became the first person charged under the provision of the law that made it illegal to gain unauthorized entry into a federal computer. He was convicted, but the judge decided to be lenient because it became pretty clear that Morris really hadn't intended to cause this much damage. So he was sentenced to community service. He ended up going back to school, not to Cornell this time. He went to Harvard, got his PhD in computer science. He made a fortune in the computing industry, and he became a tenured professor at MIT and has never spoken publicly about what happened. Now, I don't want you to get the idea that my book is entirely about things going wrong. There is a really fun chapter on the Roomba and how it learned how to navigate your living room. I can't have a Roomba because my cats lose their minds, but anyway. In another delightful chapter, David Castle, the chapter, in fact, that gave the book its title, David Castle talks about code comments. Now, comments are basically little lines in the code that are not directed to a computer. They're directed to people, to programmers. They're succinct explanations for why the code is doing something in this spot. Sometimes that might even be sort of code to yourself, to remind yourself of why you did something this way, sort of like trying to help yourself read your handwriting many years in the future. Now, normally, comments are pretty prosaic. You know, they're usually just something very boring. But sometimes they can offer something a little bit more, like a clear joke. Or they can unintentionally offer something more. And that brings us to 1975 and a routine chunk of code for the 6th edition of the Unix operating system. A Unix operating system programmer, Bell Labs, had written, "You are not expected to understand this." And 50 years later, those 7 words live on. But instead of warning off readers, the enigmatic comment intrigued them, and it became famous in its own right. It began showing up on T-shirts and sweatshirts and even baby clothes as an expression of pride of technical mastery, that we understand something that the rest of you do not, that I do not. Except, as Dennis Ritchie, one of the original programmers who wrote the Unix code, later wrote, that was not what was intended at all. The 1975 team simply felt that this snippet of code in question was addressing a particularly obscure problem. In 2004, he wrote, "You are not expected to understand this" was intended as a remark in the spirit of "this won't be on the exam," rather than an impudent challenge. But maybe the comment has remained so popular, despite that misunderstanding, because it speaks to a general fondness and warm appreciation for those glimpses of personality that sometimes sneak into computer code. In 2014, Silicon Valley's Computer History Museum announced that they'd received permission from Microsoft to publish the historic source code and comments for the original Word for Windows released in 1990. One Microsoft programmer begins a comment by first dubbing the section a gruesome hack. After a particularly technical flourish, another programmer added the comment, coded in line because we're God. There was an awful lot of profanity, still is. But there are other comments, too, that become sort of cherished reminders of a momentary glow of humanity in this world of unforgiving logic. Programmers may offer up a humble moment of self-deprecation or warnings about straying too far into exotic and arcane solutions. And sometimes they do both at the same time. When Unix pioneer Roger Faulkner died in 2016, a fellow programmer remembered one of Faulkner's famous comments. This is a horrible kludge or kludge, depending on how you want to pronounce it. A kludge is sort of like a sloppy fix, like MacGyver using duct tape. It is vile, it is swill. If your code has to call this function, your code is the same. Another chapter of the book looks at the Apollo guidance computer used during the first lunar landing. And as authors Ellen Stofan and Nick Partridge write, the programmer's notes to one another in the code are tremendous. There's an instruction to reposition an antenna that's labeled, crank the silly thing around, in order to safely continue off to see the wizard. There's another sequence that ends with, come again soon, and a block to control instrumentation displays was filed under pinball game buttons and lights. Another section that made it into the final version was marked, temporary, I hope, hope, hope. But the code also reflects the state of the nation and the world at the time. There's an ignition sequence that's called Burn Baby Burn, which one young programmer later said was an allusion to the Black Power movement. So even as they were preparing to go to another world, the fight for justice was at the forefront of their minds. There's a really important meta message hidden in these silent libraries of intellectual endeavors, which is that it's people who write these programs. And more importantly, that it's communities of people who write them and preserve them. There's a stereotype of a lone genius kind of hacking away, but it's an outdated pop cultural idea. Code's written collectively, though we very rarely see it that way, at least those of us who don't work on it on a day-to-day basis. Every comment is an implicit acknowledgement of that code and all the careful caretakers who may someday have to revisit it. And they may revisit your code far later than you expect. On Saturday, I talked about this book at the Oxford Literary Festival, and I made a really cheap joke about Y2K. I said that programmers had fixed Y2K, but they also caused it. And one reason I felt that way is that, as I mentioned, my mother spent a brief, unhappy period of her life working in programming, and as she was learning, she noticed the two-digit, four-digit year problem. And she asked an instructor, hey, is that going to cause problems in the year 2000? And his response, apparently, was, that's going to be someone else's problem. She told that anecdote, especially in late 1999, as a way to demonstrate programmers passing the buck. And I took it in that spirit, and that's why I made the joke on Saturday. But as the lovely gentleman who came up to me after the address told me, he had been a programmer in the 70s himself. And it had never occurred to him that 30 years later, anyone would still be using the software that they wrote. And that's a great point, because the truth is we don't just use 30-year-old code. We use 60-year-old code. When the pandemic hit and unemployment benefits were expanded in the US, people flooded state unemployment websites. Those websites were built on databases that were written in COBOL, which is a language that, as is described in You Were Not Expected to Understand This, was born in 1959. So in 2020, we were using a programming language from 1959, a language that nobody learns today. In fact, the situation became so dire that the state of New Jersey released this plea begging for retired COBOL programmers to come back to work and help them fix the system. Similarly, as Meredith Broussard writes in the book, when same-sex marriage was legalized in the US, it required changing thousands of databases. This is a process that was informally and delightfully called Y2Gay. These were databases that had been set up to only allow marriage between a man and a woman, and so changing the law meant that the databases had to be changed as well. Meredith phrases this beautifully. Computer systems are not just mathematical, they're socio-technical, and they need to be extensively and regularly updated, just like humans. You are not expected to understand this, has a lot of big ideas. But the one I really want to leave you with is that you can't look at code in isolation, which is a lesson that I think many in big tech still have not quite learned. As this book was nearing publication in the US, Elon Musk officially took over Twitter. At the time, I was still working at Slate on technical topics, which meant that Musk also took over my life, as he would regularly tweet things at 8 p.m. on a Friday, and then I would have to try to cover it. One of those times was when he said that he only wanted people who were hardcore to stick around at his new Twitter. Many of Musk's initiatives were, and probably are, I don't pay quite as much attention now, focused on code, on this prioritizing code above all as this pure distillation of technical expertise. At Twitter 2.0, he said there would be far less focus on humans and far more emphasis on code. Journalist Casey Newton reported that the day after Musk took over Twitter, engineers were told to print out 50 pages of code they had written in the previous 30 to 60 days. Soon after that, though, a Slack message went out, presumably after executives realized that it's probably not a very secure thing to have everyone print out 50 pages of code, and they were all told to actually shred them and instead bring over their laptops to show off their code. And a few weeks later, another request went out. Musk asked people who actually write software to email him a bullet point summary of what their code commits had achieved in the past 6 months, along with screenshots of the most salient lines of code. And when I saw that request, I asked my colleague Greg Lavallee, who was Slate's VP of Technology, what he thought. And he laughed at the idea. Then I made him write about it for Slate. He told me that there are huge problems with the idea of looking at a screenshot of a piece of code and then using it to judge an engineer's ability, which, in a lot of ways, goes back to the first criticisms of the project that led to this book. Looking at code in isolation is not really going to tell you very much. If you just ask for the code, you're not getting the context for why it was written at the time and who was writing it. But perhaps more importantly, as Greg wrote in Slate, code is written by teams, and Musk was asking for presentations from individuals. Musk has also fired many of the people from the softer side of Twitter, those who work on government policy, on democracy, on human rights, and on fighting misinformation. So at a time when the world needs more humanist thinking and technology, Twitter is now going in the other direction. One of the risks of focusing on code more than humans, as Ethan Zuckerman pointed out when we did an event in Los Angeles recently, is that the very process of programming may be changing very soon. You've probably heard about Chat GPT, the generative artificial intelligence system that you can ask to write a short story about clowns in the manner of George Orwell, or ask for romantic advice, which seems like a terrible idea, and yet people are actually doing it. But you can also ask it to write a small, simple program, and usually it'll work. Now, prediction in technology is a really dangerous game, but this suggests that it's possible that in a decade or so, programming jobs could look very different than they do now. But even if an artificial intelligence is writing code, I would argue, it's still going to be human in many ways. Remember how the police beat algorithm and its predictions were reflections of human biases boiled down into code and then projected forward again. Generative AI, like Chat GPT, is built on humans, specifically what we've written online. We don't know exactly what trained Chat GPT, but I would bet it was an awful lot of Reddit, for instance. That means that even when written by an AI, code is a reflection of humanity, of our values, of our assumptions. It represents our priorities and these biases, and it governs our lives in ways large and small. So I think it behooves all of us to keep in mind, whether we write code or not, that code is human and humans need to understand code. Now, that doesn't mean that you have to understand what any given line of code means. But I think that to be an active participant in 21st century life, you are expected to understand the power that code wields and how it's come to be. Thank you.